Great. Okay, cool. All right, well, happy Pi Day. Welcome everyone that's in the classroom now and that's online. I know there's a dozen or a few dozen people in the chat already. We've been working really hard on getting something to do today on Pi Day for all of Pi Day for literally 24 hours, right? We're going to be talking about discrete math mostly, but there's a bunch of other nice highlights like number theory and so on. I'll show you on the next slide real quick. Before I do anything, I want to introduce as many of the speakers that we have here right now that are going to talk to us today. Everybody here is a graduate student at the University of Montana. Well, I guess I'm a faculty member, but these are some of our grad students. First is Molly, who's going to be up first. And then hop in here, there's Alec. Excellent. And we got Nana. We're not going to all fit, but that's okay. Michael's coming in this frame here. Excellent. Hi, Michael. And we got Hannah. And then we have a few other special guests that are going to show up a little bit later, but these are a bunch of our speakers, so excellent. Okay. All right, so before I hand it off to Molly, who's going to be our first speaker, I just wanted to give a quick, one second. Audio is great, I see, awesome, okay. A quick overview, excellent. Okay, I can even turn the camera off here. No camera. Hope you can still hear me just fine. I can see the slide over here. So this Pi Day is going to have a big graph theory bent to it. I think there's going to be 9 hours across the whole thing at various versions of graph theory. We're going to start off with an intro to graph theory that will culminate in sort of answering the question that you see here, phrased in a little bit different way, that how can we color a map in sort of the canonical way that we do so that countries don't have the same color and keep the number of colors down. But you'll learn a lot of other graph theory along the way. Later, we'll hear about spectral graph theory, which is sort of the idea of what can you use from linear algebra to say something about the structure of a graph. What are the eigenvalues of a graph, whatever that means, say about the graph. Then we'll talk about coarse graph theory later on as well. That's sort of the third portion on graph theory. And I've phrased this as how does a graph look from maybe far away? And that's a pretty nebulous question, but yeah, no pun intended. But when we get there, you'll get a really good, especially this will be really great for you, those of you that are experts in graph theory or in discrete math. This is a pretty new and emerging field, so it'll be really fun to see some of that material. Number theory is also totally new. One of the highlights here is how can we send secret messages using prime numbers? Remarkable thing. And then we have some of the old classic favorites, counting, induction, binomial coefficients, although there's a bunch of new material in those as well. Okay? All right, so happy Pi Day, everyone. And without further ado, Molly is going to come up here and talk to you about graph theory. Yay. Okay, this is funny. Right, yeah. The audio is like pretty good that it's, you know.
No, we're going. All right, there we go.
And pocket or whatever is comfortable.
All right, hello everybody. As you heard earlier, I'm Molly. I'm, if you're interested, a first-year PhD student here at the University of Montana, and I'm studying topology, but graph theory kind of overlaps with it weirdly. So today I'll start off with like giving sort of a motivating example. The first thing I'm going to talk about is the 7 bridges of Königsberg. This is traditionally like thought of as the first sort of real graph theory problem that was posed as well as answered. So just a little background, this Königsberg, Prussia, was a real place, but is now in Russia. It started out spanning this river, which I think you can now see on the slides. There you go. So we have this sort of like land configuration, the sort of skinny like parts that are around the land masses is the river. And the people in this town said, okay, we should probably build some bridges to cross to the other chunks of land. And so as time went on, it sort of became a question about like, is there a way that I can walk around the city while only traversing each bridge once? And so this was a question that people were asking themselves and like trying to do like a little tour around the city while only crossing each bridge once. And it sort of seemed like they couldn't do it. And so the first sort of formal proof that you perhaps cannot was posed by Euler, and I think he did this in 1736, so a long time ago. But in doing this, he sort of cooked up a whole new field of math, which we call graph theory now. So to explain a bit about how his idea went, we have this landmass A, which is sort of an island, and then there's this like landmass over here, D. And then we have the 2 banks of land. So like all of this area is the river. I'm just going to label these according to the graph that we have on the screen. So this is A, this is D, this is B, and this is C. And so the sort of bridges are configured in a way such that we have one bridge from D to B, one bridge from D to C, two bridges from A to C, and two bridges from A to B. So if I want to think about this more generally, if I'm walking around and I only care about like not traversing bridges more than once, I can like start here, traverse this bridge and walk around, do whatever I want on B, but eventually I'm going to have to cross a bridge again, right? So just to simplify this problem a bit more, we can just think of each of these sort of land masses as like one little entity, and we'll draw them as little dots. So here's our landmass A, here's C, here's B, and here's D. So what we want to do is now model like the connections between each of these land masses, which is just the bridges. So all I'm going to do is connect each of these dots according to which bridge connects the two land masses. So for instance, I'm going to start with D because it has the simplest sort of connections. D is connected to B by a bridge, so I'm going to draw a line from here to here. Cool? Yes. Okay. All right. Let's move it over then. There we go. How's that looking? Better. Great. Okay. Similarly, we also have a bridge from C to D, so we'll draw a line there. And I'm missing a bridge. There's also a bridge from A to D, by the way. That's kind of important. Okay, so we also have a bridge from A to D. Great. So now all of the bridges from D are covered, and I can just worry about these ones. We have two bridges from A to C. So I'm going to draw one like this, one like this. It doesn't really matter, like this isn't what we call a directed graph. So I'm not limited about whether I can only cross this bridge like this way versus this way. If I'm here, I can cross it this way. If I'm here, I can cross it this way. I just can't do it twice. And then I'll draw a similar sort of picture from A to B. So here's our simplified picture. And I'm just going to assume that like I'm on a walk around this city. Say that I started at C and I'm like, okay, I want to cross this bridge to D. All right, I'm at D now. Now that I've crossed this bridge once, I can't cross it anymore. Cool. I still want to complete my walk though, so I'm either going to choose this bridge to cross or this bridge to cross, right? Does anyone have a preference of which landmass we visit next? No? I'm going to go with B. Great. So I've walked from C to D and then from D to B. But that still leaves this bridge here that I haven't crossed yet. But if I make my way back to this bridge, suddenly I'm trapped at D. I can't cross this bridge again, and I can't cross this bridge again. So that means that I can't traverse back to D unless it's at the very end of my route, which is something interesting. So we'll talk more about like what conditions exactly make it possible to do this walk in a nice way. Now, perhaps. But before we get to that, I want to define formally what a graph is. So if we look at this graph, actually, no. Do I want to do that first? Perhaps I want to do. Yes, I want to talk about what a graph is. So I have this graph here. This is a graph, by the way. I have modeled these things as little dots and the connections between them as these little lines. So from now on, I'm going to call these little dots vertices, and I'm going to call these lines edges. So the edges are just the connections between the vertices. This is how we model like the connection between various items in our problem. Another important thing to know is that we need to know how many edges is connected to each vertex at any given point, and we call that the degree. So the degree of C, for instance, is 1, 2, 3, because we have 3 edges coming off of it. So this has degree 3. Now, if we look at A, we have a lot more edges to worry about, but if we just count them up, it's A is equal to 5. We have 1, 2, 3, 4, 5. So the degree of A is 5. Cool. Does everyone like understand how we sort of like count these things up? Cool. Great. So now, generally, we sort of like talk about graphs in this way. Some other examples of graphs that you are very familiar with is the internet, with web pages and hyperlinks between the web pages, social media between like connections with you and your friends. We can also think about like sort of biological networks as graphs, which is something that I hadn't considered before because I'm not really a science person, but my friend is a neuroscience person, and I was talking with her about it, and she said, well, you can think of the neurons and synapses as like the neurons are our nodes and the synapses are the connections between the nodes. Cool. Another bonus is you can think of connections between people at a party as a graph as well, and we'll get back to that later. So now I have another problem for us to do. I'm going to erase. Before I erase, are there any questions about this? Feeling good? Great. Okay. So here I have cooked up a problem for us to try and like get more of an intuition about what a graph is and what it can do. So our problem here is that we have 3 of our speakers who are taking classes. Our speakers are Hannah, Nana, and Anna. They are real. You'll see them throughout the course of the day, so shout out those guys. We have the problem where Anna is taking spectrograph theory and optimization, and Nana is taking optimization and representation theory, and Hannah is taking spectrograph theory and number theory. So a way that we might want to model this is say, okay, well, I need to know which students are taking which classes. So the way I'll start out is, okay, here are our students. I'll have one vertex for each student. So this is Nana, this is Hannah, and this is Anna. Cool. And then I'm going to model the classes as also nodes. Also, I'm going to use vertices and nodes interchangeably for the throughout. That's my bad. So we have the classes. The options are, what was the first one? Optimization. I'm going to abbreviate for time. Number theory, spectrograph theory, and finally, representation theory. Okay, so these are our classes. These are our students. The edges that I'm going to draw are going to tell me which students are taking which classes. So if Nana is taking representation theory as well as optimization, then we draw these 2 lines. If Hannah is taking number theory and spectral graph theory, we connect those 2 lines. And if Anna is taking spectral graph theory and optimization, we connect with those 2 lines. So here's a graph modeling some things. You might be wondering why this is particularly helpful, but it turns out that it's like huge in scheduling problems. So pretend we're at a university. Surprise, we're at a university. A lot of classes are happening at the same time. We have a limited number of rooms. It's a similar problem to this. It turns out that we can say, okay, well, if this class and this class are happening at the same time, but Hannah needs to take both of them in order to graduate, how can we move the schedule around so that Hannah can take both of these classes, but also so that, who else is taking number theory? Nobody else is taking number theory. Who else is taking spectrograph theory? So that Anna can also take spectrograph theory at the same time. So that's just one sort of problem where this might come in handy. I'll talk more about that later. It has to do with graph colorings. So this is our first sort of example. And I sort of jumped the gun on some definitions, but to review, we have that these are vertices, these are edges, and the degree of each vertex is how many edges is connected to a vertex. Cool. Great. So another important definition that we're going to need is about connected versus not connected graphs. So for the remainder of the talk, I will be mostly concerning myself with connected graphs. And we define a connected graph as follows. A graph is connected if every vertex in this graph is connected to every other vertex in this graph by some sort of path of edges that we can draw. And if a graph isn't connected, we say it's not connected. Simple enough. So the first sort of problem that I have for us here regarding connected graphs is we're trying to use this definition to determine whether each graph is connected versus disconnected. So if we take a look at the first one, I'll try my best to recreate it here. I might not do the whole thing. I'll stop here. So my question to you is, do you think this graph is connected? I'm seeing some nods. Cool. So I agree, this graph is connected. The reason why is if I choose any two vertices on this graph, say these 2, I can follow some path of edges to connect the 2. And I can do this with pairwise with any of these vertices. And then our second example is this sort of graph. Is this connected? Can someone tell me why? If I chose that one and that one, I can't make a path between them. Okay, simple enough. It feels pretty intuitive, right? When we think of graphs, this is typically what we think of, right? But sometimes these can pose a problem, so we still have to keep it in mind. Okay, so now we have our first theorem. And before we really get into it, I have to say some extra words about some things. So our theorem states that a connected graph G has an Euler-Tor if and only if every vertex of G has an even degree. So if we think back to the graph of our bridges from before, which I will redraw. Looks familiar? Okay, so if we just take this theorem to be true, we want to show that there's like, okay, all right. Let me think how to say this. Cool. Imagine my first one where I forgot a bridge. Great. So if we notice, like each of these vertices, well, even that's not great. Cool, let's take a simpler graph. Let's take this one. Cool, I want to like go between 4 landmasses. There's some bridges. This is great. An Euler-Tor we define as a walk along all of these vertices where we only pass each edge once. We start at this vertex and we end also at the same vertex. So I'll just write those conditions down. So it starts and ends at the same vertex. And also only traverses each edge once. Okay, is that sort of making sense about what an Euler-Tor even is? Cool, I'm seeing thumbs up, that's great.
Should we say each edge exactly once?
Yes.
Home?
Yes. Precisely once even.
Even better. I don't think it was incorrect.
No, it's to clear up any potential confusion, yeah. All right, so now if we really do think back to this graph, we said that we have some odd number vertices here, like there's some odd degrees happening. So that means that we probably can't traverse each edge only once, right? Cool, so now I'm gonna prove that that's true, and I'll get rid of some stuff to do that. Okay. So I denote the proof of the forward direction as this thing. Because this is an if and only if statement, we have to assume the first part and prove the second part, and then we have to go backwards as well. So in case you haven't taken a proofs course before, that's sort of the general idea. So first we're going to assume that G is connected. And also that every vertex has even degree. I'm going to abbreviate vertex as VRTX for the future. So we said that if our graph is connected and every node has even degree, then if I like find myself at this point, I had to have traversed in by one edge, and then I'm also going to have to leave by another edge. So it wouldn't be possible for me to have a third edge, or else I can't get back to where I was, like I said earlier. So in that way, we say that each visit to a vertex is preceded by an incoming edge and followed by an outgoing edge. That means that like any number of visits to our vertex, i.e. any number of edges to our vertex, has to be even, or else we can't do the walk nicely. So I'll just write that down. Are there any questions about this? Do we believe this statement? Feeling good? Great. Okay, so that's our forward direction done. So now we just have to do the backwards direction. So for this one, we're still going to assume that G is connected. But now we're going to assume that we have an Euler tor. Okay. So actually, is that what we want? I sort of did this backwards, I fear. However, I'll just switch these. Okay. Yeah. So I did the backwards implication first, my bad. All right, so, all right, here we are. G is connected and we have an Euler tor there. Then wait, actually. I'm all turned around.
I think you proved what you have written down there, right? You have an Euler tor in parallel 3D.
Yes. So.
Right, since every visitor
Yeah.
received by edge.
So that is the backwards direction.
Direction is. I think the direction is forward, and you went from Euler toward.
Cool. Great. Sorry, guys, for the complication. Technical difficulties, you know? Okay. So now we have that G is connected and every vertex has even degree. Great, that's my assumption. Now I want to show that there has to be an Euler tor. Great. So the first thing we do is we say we want to define some sort of path where we use the maximum number of edges available to us. In graph theory, we call that a walk, so a maximal walk, perhaps, around G. So we want to define a walk around our graph G. So all that means is that we've used every edge like possibly available to us. So we also want to say that we only do this walk using each edge once. Cool.
Here's probably not defined with each edge at most.
Yes, at most.
Best we can.
Yes, because we want to use as many edges as available to us, but if one isn't available to us, then we can't traverse it. Great. So since we've used every possible edge available to us, I'm moving here now. Whatever vertex we end up landing on, say it's this one, we've already used this one because it was available to us. We've already used this one because it's available to us. There's no additional edge that we can traverse anymore because we've used all the edges that were available to us. Cool. I'm going to denote the vertex that we end at as V. Okay. So since the degree of V is even for every vertex, then there is nowhere else for us to go. And in fact, because there's nowhere else for us to go, we must have started there too. Because if we're coming in from that edge and there's no other edge to leave from, our degree is even. I had to have like left at some point, so that means we had to start there too. Cool. Great. So now we've established that we've traversed as many edges as we possibly can at most one times. And we've also started and ended at the same point. So by our definition, we have this part. And we need to say that it traverses every edge, not just the ones available to us, but all of them. So if our walk does hit every edge, automatically, we're done. But if it doesn't, we have to like figure out why. So board space, I think, will be okay. So if we don't start out using every edge, because our graph is connected, there has to be an edge connected to some vertex that we didn't use. So like, say it's this one, maybe. Perhaps there's an extra edge there that we just didn't use. So if that were true, this would have degree 3. And that is a contradiction because we said that every vertex has to have degree 2. So we simply just can't have that we didn't traverse an edge because like we couldn't have gotten back to our walk in the first place if we did. And so that's our contradiction. I'm not going to write that all down because it's a lot of words. But does everyone follow the argument? Cool. Feeling good? Great. So this is a fun little proof. I really like Euler's tors. They're kind of like silly to me. But next up, we have like a sort of problem that models why this could be useful. It's called the 5-room problem, which you can now see. So our 5-room problem says if we have this sort of configuration of rooms and there's a door on each wall connecting the rooms and also connecting the rooms to the outside. Right, QED count. 1. Excellent, we're well on our way. So if we have this sort of configuration of 5 rooms, here is our house, here are our 5 rooms. You see that on the screen? Great. So I'm going to label this A, B, C, D, E. And since we have doors to the outside, we also have to consider that as its own room. I'll call it F. So if we have doorways connecting each of these rooms, then we have a doorway here, 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 here. These are all of the possible doorways. That's a lot for my eyes to look at. I want to model it as a graph. Cool. Does anyone have a suggestion of like what my node should be? The rooms, great. So I'm gonna start drawing some nodes here, roughly in the same configuration as our house, but it doesn't have to be. And here's F. So and so we have all of our vertices. Our edges are just going to be like the doorways that connect each of these rooms, right? So starting with A, we have one door connecting A and B. We have one door connecting A and C, one door connecting A and D, and 2 doorways connecting A and F. So I'm going to draw those this way. Cool. Similarly for B, we connect to D, E, and 2 doorways for F. Great. We have connection from C to D, connection from D to E, connection from D to F, and 2 connections each for C and E. Great. How is this going to help me solve the problem about whether or not I can walk through these rooms nicely, only using each doorway once? I'm just going to use what we just proved. So what we just proved was we have an Euler tor if all of our edges are of like even degree. So pick an edge. Let's figure it out if we satisfy our conditions, right? So at vertex B, we have 1, 2, 3, 4, 5 edges. That seems like a problem to me. Guys, I don't think we can do it. I fear we cannot do it. So since our degree of B is equal to 5, we have that there's no Euler tor. But remember that our Euler tor required us to start and end at the same vertex. So a natural question is, can we do this if we allow ourselves to not start and end at the same vertex? Say I started at F, and I wanted to end at B, only using each doorway once. What then? So my answer to this is going to come in the form of a corollary. So is everyone comfortable with this, first of all? Great. You might be wondering what we call an Euler tor that we don't require to start and end at the same point. We call it an Euler trail. Love it. So just as a definition for you, Euler trail I'm just going to define it in terms of an Euler tour because we know what that is. So an Euler tour without the requirement that we start and end at the same point. Great. So my corollary here says that if we have a connected graph G, and that has an Euler trail that starts and ends at some vertex x, well, no, starts at vertex x and ends at vertex v, then x and v must have odd degree, but all of the other vertices must have even degree. Okay. So let's start with our proof. This is an if and only if statement again. I'll try not to get my directions confused this time. So the forward direction will say, we're supposing that we have a connected graph G with an Euler trail that starts at x and ends at v. So connected graph. Okay. I'm going to draw a quick picture because pictures are great in graph theory. So if I want a graph that has some sort of Euler tour, what did I draw here? Yeah. Okay, here's my x. I want to start here. And here's my v. I want to end here. We have an Euler tour by assumption. Just trust me on that. And it starts at x, ends at v. Great. So if we have this sort of trail that we can follow, for any vertex that's not x or v, we have to have that the degree of that vertex is even. Simply because if we were to delete these two and ignore them, we need to still have an Euler tour on these 4 points, which requires us to have even degree. Okay, so let's write that in words. If y isn't equal to x or v, but is in G, this symbol means in G. It just means that that's a point in that graph. That's all that means. Is on the trail. We must have even degree. Okay. However, if we're starting at x and we leave x, right? We go to some other vertex. It has to be the one right next to it, by the way I've drawn the graph. We have to, in order for it to have odd degree, we have to either leave it and never come back, or it has to be our last stop on our trail, right? So similarly for v, we also have to have that we either go into v and never leave, or we leave v and never come back. So because of that, we can make stops along the way if we were to draw our graph differently. But if we were to revisit, and we started here, we were to revisit, we would have to get back to our main graph, so we would have to go out again. So even though we do have like a double edge sort of visiting x, we still have to have that third edge that's leaving for the last time or coming in for the first time. Cool. So this shows that x and v have to have odd degree, which is exactly what we wanted to show in the forward direction. Feeling good? Great. So I'll start the backwards direction here. I'm sure my board management will get better as we go on, but for now it'll be a disaster. So now we're going to suppose that x and v have odd degree, and every other vertex has even degree. So we also still want to assume that our graph is connected, because otherwise we can't really talk about this. I secretly already stated this argument before. However, to say it again, if we were to create a new graph based off of this one that we already have, in order to make x or v an even degree, we're allowed to just like sort of add a vertex out here and make a little connection between them. So I'll call this u. I'll call this edge xu and this edge uv. Does that make sense, everybody? Cool. So this is some new graph. I'll call it g prime. And so now we can observe that like x has an even degree and so does v because we've added, this new sort of edge to it. Cool. So because all of our vertices now have even degree, we have an Euler tour on this new graph. Great. Great. So now I have to think about what we want to do. Okay, yeah. Now that I know that we have a tour around all of these edges and vertices, I can just say, okay, delete it again, and now get rid of also its edges. And suddenly we have a tour on everything except for these two, and these two are of odd degree, which means we have an Euler trail. And that's how we do it. It seems a little bit silly, kind of, because you just sort of like say, okay, make it a tour and then get rid of it again. But this is how it goes. Yes?
In this picture you had, what if you added an edge between x and v instead of going via?
I also had this question.
Seems like that would work too, right?
Yes, it does. Cool. Yeah. I made it harder than it needed to be.
No, I don't think you made it.
But here we go. That's our proof. So now we have that corollary. Very cool and fun.
I think that counts.
It does count as a QED. I keep getting hand signals back there, and they're very helpful. Keep it going. Thank you. Cool. So now a question you might be asking yourself is like, okay, if I have like this really big graph with a ton of vertices and like a bunch of connections between them, is there a way that I can find an Euler tour in that graph? The answer is yes. We have an algorithm for that. It's called Fleury's algorithm. So I will be drawing some preliminary pictures before I actually prove this, just to get an idea of what we're actually talking about. So say I start out with a graph that looks sort of like this. I'm not going to make it really big and complicated because I'm only a human and not a computer. So I have these connections. And there's my vertex v. Our algorithm says if we start with an arbitrary vertex, we can traverse edges to just construct the walk that we want that will give us a tour. And the way that we do that is starting at v, if we traverse an edge, say I go here, we delete that edge. So I'm going to denote deleting an edge as sort of like marking those out. So say I follow that path. We also have an additional condition that says we don't want to traverse any edge that is a bridge on a graph. So new definition time. A bridge is just an edge that if we deleted it, it would disconnect the graph. So for instance, if I were to choose to travel along this one and I disconnect it, I have this component that's still a part of G, but it's completely disconnected from this. So I don't want to traverse that edge by this algorithm. Okay, so I'll draw that back in. By the way, I've drawn this graph. We now only have one other option. We're going to traverse up. I'll delete this edge. Cool. I only have one option. Delete this edge. Cool. I only have one option. Delete this edge. Cool. And because I want to end this in a timely manner, I'm going to traverse this edge because we could traverse this edge potentially, although it also might disconnect our graph. So maybe we can't. Anyway, if we think about the edges and vertices that I have since deleted, and we just sort of follow the ones that I've deleted, it gives us a Euler tour, starting and ending at V. That's sort of how this algorithm goes. The proof is a bit involved, which I'll start now. We have a theorem that says Fleury's algorithm really does produce an Euler tour. So the proof for this sort of starts in the middle of our problem. So say that we started with that graph, and I shouldn't have erased it really, but if we started where we had already deleted one edge, now we have the choice of traversing some edges. We need to check some cases to make sure that everything works out well. Okay. So we're going to let H be the remaining graph that we have to traverse. So after I've deleted an edge, everything left over. Great. And we want to sort of like put ourselves in there at an arbitrary step in the algorithm. Cool. So suppose the vertex that we're on is just like labeled U. I'm just going to call it U for ease of, knowing where we are. Cool. So from here, if we think about like what our graph sort of needs to look like, our original very beginning starting position, V, where we like started our sort of tour type thing, and U are now going to be the only two vertices of odd degree. And that's because we've sort of like deleted an edge from each of them. And that's why. So suppose to a contradiction, we're going to assume the opposite thing is true. So I abbreviate that as TAC. Keep going. That U is connected to two bridges, in which case our algorithm is like really scared because we don't really have an option about whether or not to traverse a bridge or not. So yeah. I'm going to use incident here because connected is a definition that we use. So incident. So just for a visual, here's where I'm at, and this is U. Say we have this vertex over here and this vertex over here. We'll call this W prime. And if we traverse this one, there's some other edges over here where if I were to delete this, it would disconnect my graph from previously. And then similarly over here. Cool. So like, I don't really have a choice. I have to traverse one of them. So let's see what happens. We can also say that our original starting vertex V is not part of this configuration, but I'm going to denote this bridge as UW prime, no, as UW, and this one as UW prime. U's and W's are too easy to interchange. Okay. So, once we delete this edge, no, we don't delete that edge. Note that this vertex has odd degree as we've drawn it right now. And so does this one. So by a secret, very cool thing called the handshaking lemma that you don't know about yet, but will soon, we have that there exists some other vertex in H connected to W because that's what the handshaking lemma says. Trust me on it. So let me be really clear in how I write this. So our vertex W has odd degree in our bigger graph. And then by our handshaking lemma, which you will figure out what that is soon. Abbreviations. There has to be another vertex W, vertex in W, which is also in H. But that's going to be a contradiction because we said that our only vertices of odd degree are U and V. So So this argument might not be super clear to you because you might not know what the handshaking limit is yet. We'll get there. And like the similar argument follows for if you were to choose W prime, it's the same thing. So that case is sort of thrown out because we've got contradictions. So we know that that can't really happen in this algorithm. Okay. So now we have to concern ourselves with like, okay, well, if U is only connected to one bridge, what do we do? I'm moving up here. So we have no choice but to traverse that edge between U and W, which we know is a bridge. So if we do it, it'll disconnect. But after traversing that edge, we're sort of like stuck in this new sort of cutoff part of W. So when we delete that edge, we're left in W, but this is still a connected graph. We'll call this sort of disconnected component of the whole graph, but in itself connected W. Okay. Capital W, these have been lowercase so far. It's not really clear, but anyway, they're different things. So now what we want to do is, because the algorithm that we're following will never disconnect the remaining graph because all of our vertices have to be even by our assumption, we can always have a vertex left that we visited, and we have to eventually walk along every edge. So sort of to put that into words. So to more concisely put what I said poorly before, the remaining graph that's left over, the algorithm that we use will never actually disconnect the remaining connected graph. And so all of our vertices will have even degree because if we enter a vertex, we have to leave it again. And so eventually we have to walk every edge. So that gives us a full tour and we're done. Okay. Any questions? Feeling good? Cool. All right. So yeah, it is another QED. Gosh, I'm bad about my QEDs. Yeah. All right, we're already at 3 in case you're counting, which we are. Okay, so now that I've used the handshaking lemma, you probably want to know what it is. I'm going to do that now. So it's sort of an important thing in graph theory. It comes in handy quite a lot. Our handshaking lemma says that the sum of degrees in a graph has to be even. And in fact, it is equal to twice the number of edges. So it might seem like a sort of weird thing, difficult maybe thing to prove, but it's actually not so hard. What we have is, if we have some graph, like whatever, doesn't matter how it's connected. If we think about like sort of counting vertices versus counting edges. The number of vertices in my graph that I've drawn here is 6, I believe. So call this G. Now, if I want to like count the number of edges, we sort of need to know that like we need to observe, I suppose, that each edge is shared by 2 vertices. So if we're trying to determine the number of edges based off of the number of vertices, then we have to say, okay, well, I count each edge twice for for each vertex that I have, which means that like the number of edges has to be 6/2. No, not that. Twice the number of edges, 3. The number of edges has to be 3. That's also wrong. Hey guys, I'm messing this up. All right. Okay, let me just prove it. Okay, if we sum, yes, I see my error. If we sum the degrees of the vertices, we sort of count each edge twice. So for instance, if we look at this vertex, we have 2 edges. So the degree of this is 2. But if we look at this vertex, it also has 2 edges. The degree of this is 2. But they share an edge, and each degree counts that edge once. So we sort of have to account for that. Each degree counts each edge twice. So if we were to sum up all the degrees of all of our vertices, this is summation notation. That means we're summing from 1 to however many we have of whatever we want to sum. This is going to be equal to twice the number of edges of our graph. It's just a double counting argument. Cool. Is that okay with everybody? Great. Seeing nods feels good. Super okay with double counting. It's fine. We can deal with it. It's okay. So now we have a problem that sort of uses this. Our problem statement is as follows. Say we're at a party with 101 people. We want to show that someone at the party has to have an even number of friends there, okay? So if we sort of like take into account everything we learned so far, specifically the handshaking lemma, if we sort of like model our graph as the dots are people and we have edges connecting them somehow, it doesn't really matter how, and there are 101 of these dots, I don't want to draw all those connections and count up the number of, edges or whatever. Like, I just don't want to do that. But instead, we can just use the handshaking lemma. So if we have that we're summing from I = 1 to 101 of the degree of each v sub I, we need that to be twice the number of edges. So the way I'm really going to prove this is I'm going to assume that everyone has an odd number of friends. And we have to show that that's not going to be true. So assume okay. If that's true, then the sum in here, each of these is going to be odd. And we're summing over an odd number. And using some math and stuff, we know that if we sum an odd number of odd numbers, we get an odd number back. Yeah, it's crazy. It's actually crazy. The proof of that, I think, was in proof class, intro to proof, yeah. Whatever. So odd degrees. That's going to be equal to an odd number. Uh-oh, we said that the sum of all of the degrees of the vertices has to be even, because that's what that means. So we have a contradiction. Since I assumed that everyone has an odd number of friends and we showed that can't be true, at least one person has to have an even number of friends there. And that is some mathematical logic for you. How are we feeling? Good? Great. Okay. I'm convinced. So now we have a couple of corollaries that follow from the handshaking lemma. These are going to be kind of fun and actually useful. So I can erase this. And just so I remember what it is, I'll put it up here. = 1 to I = 1 n degree vi is equal to 2 edges. Great. Okay, so my first corollary says that a graph has an even number of odd degree vertices. So let's prove it. Again, we're going to use contradiction. So suppose that we have an odd number of odd degree vertices. Then when we sum them all together, it's going to be odd again, just by like what we just did. Uh-oh, we've contradicted the handshaking lemma again. So we have to have an even number of odd degree vertices because math logic. Great. Cool. This is just like the generalization of the problem we just did. And my second corollary is going to say for every odd degree vertex, there has to exist some path of edges that we can take to another odd degree vertex. Once again, we're at 5 QEDs. Hooray. Fantastic. So to prove this, I'll turn the page. Okay. So I'll label this as 1, I suppose. This is 2. We're going to pick an arbitrary vertex of our graph. And then we're going to pick a subset of that graph so that we have a path connecting, well, containing, I guess, our vertex that we picked. So our vertex can be anywhere on that path. It just needs to be in there. Great. So this path has to have total degree even because of our handshaking lemma, because it's also a graph, by the way. Great. So this is only possible, of course, if our subgraph contains another odd degree vertex, because we know that our odd degree vertex, the odd degree, has to have a partner so that like when they're added together, they get an even number because of how numbers work. Cool. Great. Is everyone convinced that that works? Feeling okay? All right, cool. So now we have a really fun problem that I actually very much like. You might have heard of it before. It's called the mountain climber problem. The problem statement is as follows. We have this sort of mountain range, and we have 2 hikers on either end of the mountain range. And we want to show that there is a path along those mountains so that if the hikers are staying at the same, once again, QED, I'm going to keep forgetting. So that if the hikers are staying at the same altitude, they're going to eventually meet on the mountain range somewhere. So I'll just draw a little picture for us to reference. It might not be the same as the slide, but it'll be similar enough. Okay.
The beauty is that it shouldn't matter.
Right, exactly. And this is much easier for me to do cases for. So say we have a hiker here and a hiker here. Okay. From before, the number of odd degree vertices has to be even, which means like this is an odd degree vertex and this is an odd degree vertex. If the hikers can only go up essentially from here, they don't have an option to like go anywhere else. So we only have an outgoing edge for each of those 2 nodes. Cool, odd degree. So since we only have these 2 odd vertices by how we've drawn this graph, by the corollary that we just did, we should have that those 2 things are connected by a path so that the hikers will meet at some point. That's just by our corollary. So If I draw a backward Z, that means there exists. So from our corollary, we have that they have to meet at the mountains somewhere, in the mountains somewhere. But the remaining question is like, can they do this while staying at the same altitude as each other? My answer is yes. Because all we have so far is like, okay, if y is going like, maybe y hikes all the way to here and x hikes all the way to here, they're gonna meet, but we have the additional like thing that like they need to be at the same altitude at all times. So my suggestion to you is going to be, okay, make a note of where every peak and valley is on this graph. And add vertices where those horizontal lines intersect those lines. So we're going to add vertices here and also here. Again, I probably chose a bad example, might miss a few vertices here, but the idea stays the same. So if we do this, then if we sort of think about like what's really going on, now we have vertices from either side. They're at the same altitude no matter what, which is good. We're almost there. If we follow these paths, say x and y star, okay, they move up one, great, we're still at the same altitude. This hiker goes here, we're still moving up, uh-oh, this hiker has to move down now. So we have to move backwards, but that's okay because this hiker can just move backwards with them. Then we move down again, back up, and eventually we do that and we meet at the peak actually, which is kind of a fun fact. But just by following that sort of, you could call it an algorithm if you really wanted to, we get exactly what we wanted. And so that's sort of, we use the handshaking lemma and secret here, but it was really like the corollary that we used. Are we feeling good about the fact that this is true? Great, okay. Moving on, we get to the really fun stuff. We're gonna be talking about graph colorings, hooray. So the first sort of thing that we need to know is a definition, of course. So if we have some graph, we want to be able to color the vertices in a way such that no two vertices that are adjacent are going to have the same coloring. And the minimum number of colors that we need to do that is what we call our chromatic number. We denote that as chi of g, which looks like an x. So for instance, this graph would have chi of 3, because if I were to color this one, say colored 1, this one is colored 2. If I wanted to color this one 2 as well, that would be a problem because we would have an edge connecting those two. We can't do it. If I wanted to color it 1, we have an edge connecting those two. We can't do it. So we have to have a third color there, that third vertex. Cool. So just some examples of some graphs. This one might look a little bit familiar from earlier. This is the leftmost one on our slide. We have 3 vertices here, 3 vertices here, and every possible connection between all of them. Did I mess up? I messed up. Yes, not the sides. You're so right. Thank you, Hannah. Cool. So we have all of those. Great. So this is an example of a 2-colorable graph. And the reason is, if we color this one a 1, then this one has to be a 2, right? Because it's adjacent to it. This one also has to be a 2 because it's adjacent to it. This one also must be a 2 because it's adjacent to it. However, note that because we don't have these vertical lines, we can color this one a 1. And in fact, we have to, because we colored these 2 and it's connected to all of them, we have to have a different coloring, so that's a 1. By a similar argument, we get that that is also a 1. So because we were able to color all of these vertices with only 2 colors, this is a 2-colorable graph. Great. Any questions so far? Cool. We also have on the slides some examples of 3, 4, and 5-colorable graphs. I will do the 5-colorable one because it's easiest. this is what we like to call a pentagram. And so, because we have all of these edges are, like each vertex is connected to every other vertex, we have to we're forced to choose 5 different colors. Because if I label this one 1, okay, well, it's connected to this one, that has to be a 2. But because 2 is connected to this one, but also connected to 1, we can't label it 1, we have to label it 3. And following that same logic, we get a 5-colorable graph. Does that also make sense to people? Cool. Great. So now we're getting to a little example. Anybody a fan of Sudoku? Yeah, man. Evil Sudoku. Yeah. All right. So it turns out that we can solve Sudoku puzzles using graph colorings. It's really cool. So I won't do like a full proof of this because it's quite lengthy, but I'll tell you the intuition behind it. So if we like represent our Sudoku as a graph, we'll end up with a 9 by 9 grid of vertices, right? So I'm not going to do the whole 81 dots, but I will do the 9 by 9. 6, 9. Great. So imagine that this whole square is filled in with vertices in a grid. And we're going to say that each vertex is connected by an edge if they are one of 3 things. So if they're connected in a row like this, we're going to have edges like this. And if you are a Sudoku enjoyer, you know that all of those things need to be different colors because all of our different numbers are going to be different colors. Okay. We also are going to say that they have an edge if they're in the same column. And then we have a third really fun sort of edge connection happening in each 3 by 3 grid. Since all of these numbers need to be different by the game of Sudoku rules, we need to have an edge connecting every single one of these. So it ends up being a really big star. I can try and draw it. Let's see what happens. Okay. It's definitely not complete, but essentially all of those vertices need to be connected by edges, like all of them. Okay, so because the proof is quite lengthy, I'll just say, surprise, surprise, we need 9 colors to fully color the Sudoku graph, basically. Because if we require each of these, so if we color this one 1, say, then all of these cannot be 1 anymore. And none of these can be 1, none of these can be 1. Say I say this one is 2, okay, none of these can be 2, nothing in here can be 2, all of this column can't be 2. You keep doing that for one of these 3 by 3 things, you end up that you need 9 different colors to color this whole graph. And it turns out if you have the Sudoku grid, we have enough numbers on here where we can assign 1 to be our first color all the way through 9. If you were to fill in the grid according to those colors and finish coloring the entire graph, you would get the solution for the Sudoku puzzle, or a solution for the Sudoku puzzle. There might be multiple. So there's one where there's 2. There's a counterexample. Anyway, so yeah, that's sort of how we might use graph colorings to do Sudoku. Any questions? I guess it's a bit more complex because if you're left with 4 squares that are empty, there's multiple choices there. That's what I mean, yeah. Anyway, so we have that. Any questions about Sudoku coloring? Great. Not yet. If you are interested in seeing the full proof, you can check out Sudoku Squares and Chromatic Polynomials, which is a paper by Huntsberg and Munty. And it's in the AMS edition of I don't know, volume 54 or something. You'll find it easily. It's not that hard to find. If you're yeah, it's volume 54, number 6, by the way. Okay, so now that we've talked about that, I want to talk about some new definitions. Some motivation behind these definitions. Essentially, if we have these chromatic numbers for a graph, I probably want to know what's the minimum number of colors I need to color an entire graph. So in order to do that, we need to find some new definitions, and then I'll tell you how we do that. Great. So turns out these definitions will be invariants for graphs, which means they kind of just work for all graphs, these definitions do. So First up, we have an independence number, alpha. And that denotes the size of the largest set of independent vertices. And we say a vertex is independent if it's disconnected from the rest of the graph. So visually, it looks a little something like this. Here's my graph. These vertices are independent from this graph because they're not connected by an edge. Cool. So alpha G is just going to be like the largest set of these that sort of exist. And that's sort of our definition. Are there questions there? It's pretty straightforward in my opinion, but feeling good? Great. Okay. Our second definition will be a clique number. A clique number is a little bit trickier to define, but essentially we denote it by omega G. It's like W, it's an omega. And this is the size of the largest, like, completely connected sort of component of a graph. So the easiest, that's like technically incorrect, but what I mean when I say that is if we have this graph here and all of these things are connected in this way, we have another vertex over here. Perhaps it's connected over here to this. Say we have some graph that looks kind of like this. The clique number of this graph, I will tell you, is going to be 4. And the reason is if we look at sort of this region of the graph, every vertex in this region here is connected to every other vertex. This is a completely connected little part of it. And so you might argue, okay, well, this is also, like this little region here, also has that every vertex is connected to each other, but because this one is bigger than this one, my omega is going to be 4. Does that make sense? Thumbs up? Great. So now we have a proposition about lower bounds on our chromatic number of our graph. So need an eraser? Here we go. Okay, so the statement that we have is if we have a graph with n vertices in it, then we have the following two inequalities. We have that our clique number is going to be less than or equal to the chromatic number of our graph. And we also have that the number of vertices divided by the independence number is going to be less than or equal to the chromatic number of our graph. Okay, so the proof of our first one, our first inequality is this. Cool. So remember this like sort of refers to, we have that set and it's all like, they're all connected to each other. So if we have a clique that we're getting our clique number from, then all of the vertices in that clique are going to be connected to every one of the other ones. So we have to color each vertex in that clique a different color, because if we didn't, it would be bad. Again, another example is this one. So all of these are connected. If I color this vertex 1, I can't color this one 1, or this one, or this one. So this needs to be colored 2, 3, and 4. The reason is because they're all entirely connected to each other. If I were to color this one 1, we would break our definition of, coloring. Okay. So if we have that, then all of our vertices in there must be different colors. Cool. And so what that means is that omega of G is, say, equal to some number m, then because our clique is part of a larger graph, our graph needs to be colored at least m, with at least m colors, because like if it wasn't, then if it was colored any less, we would have a problem because our clique wouldn't be properly colored. Any questions there? Makes sense? Fantastic. QED. Thank you. 2. we also want to show that our independence number alpha g, when we divide by n, is less than or equal to our chromatic number of our graph. Okay. So we're going to begin by supposing that G is colored properly. With the chromatic number many colors. Okay, so then these different numbers are going to sort of like partition our graph into different little groups. So we have this, again, same example. So we'll change it up. This is colored 1, this is colored 2, this is colored 3, this is colored 2 again, this is colored 3, and maybe that's a 1. So I have this weird looking graph, and it's properly colored because every edge connecting two vertices has different colored vertices. Feeling okay? Great. So this is gonna like sort of partition our vertices into different color classes. So like this vertex and this vertex is gonna be part of the color class 1. This vertex and this vertex is gonna be part of the color class 3, and this is gonna be part of the color class 2. So we just like sort of separate them up based on how they're colored. Great. So and the number of classes we're left with is obviously going to be equal to the chromatic number of G because that's how we partitioned them in the first place. Great. So each created class will be an independent set because if we were to like sort of delete this edge, now this is an independent vertex and it's got coloring 1. Cool. So another way to say that is that each class is going to be an independent set with at most the independence number of vertices in that set. Cool. So what we have is that our total number of vertices is going to be less than or equal to alpha of G times the chromatic number of G. And using algebra, we get the result that we want. Just divide by alpha of G. Questions? Feeling fine. Great. Okay, another QED. Fantastic. Moving right along. I'm actually, in the interest of time, I think going to skip the next slide. This is just a nice little result that says our chromatic number is less than or equal to 1/2 the square root of 2 times the number of edges plus 1/4. The proof for this is sort of just like computation stuff and making a few observations. And you might notice that it kind of looks like what we get if we were to use the quadratic equation. And in fact, you do use it in this proof. But I'm not going to show you how. You can figure that out as an exercise. Have fun with it. Okay. So now we get to this new problem called 3D bound problem. Essentially, we want to know at most how many colors does a graph need to be colored properly. So we want to show that a graph G has proper coloring with at most delta G plus 1 colors. And I will say that delta G denotes the maximum degree of a vertex in our graph. So. Great. So, proof. Cool. Just notationally making sure we have that. So if we color the vertices of a graph one by one, making sure that we like properly color it along the way, then the most the maximum number of neighbors that any vertex that we've colored is going to have is our delta G number. So cool. So say we have this graph, we're moving along. Okay, great. Looks like a constellation. Fantastic. So far, we have colored this one a 1 and this one a 2. We get to 3, and assuming that this is properly colored so far, the most neighbors that 3 is going to have is the degree of G, which in this case is equal to 2, just because of how I've drawn the graph. Okay. So we can properly color this graph with this number plus 1. And the reason is because if this is the maximum number of neighbors we have, but we only have like this one vertex connecting it, we have a 2 here and a 1 here, and then we've 3-colored this graph. So okay, any questions about this? Yeah.
So for is it delta G or is that a different?
It's a capital delta, but you can call it triangle if you want.
Degree. Is degree just like the amount of connections that have?
Yeah. So yeah, the degree of a vertex is how many edges is like connected to it, sort of. So the degree here is 2 because we have this edge and this edge. The degree here is 3 because we have 3 edges connecting it. Great. Cool. Any other questions? Feeling okay? Yes. That's a 2. Yeah. Yes. Because, and like, actually, yeah, it should be 3. But that's also fine because we could color this with 4, but it would be adding like a sort of unnecessary number of coloring. So like if we wanted to color this 4, there's nothing stopping us. We're still coloring it properly. We could just do it with less. Cool. Any further questions? Thank you for that one. It's a good one. Cool. All right. So now we have a really big theorem. Hooray. Also, QED. Great. So our next really big theorem says that a graph is two-colorable if and only if it contains no odd cycle as a subgraph. And so I'll explain some words to you because we haven't seen them quite yet. So a subgraph, first of all, is like just a smaller set of a graph that still has graph properties. So like here's a graph, hooray. If I were to only look at these 3 vertices with those 2 edges, that's also a graph, and it's a subgraph of our original graph. Okay, cool. And so, actually, coincidentally, if I just look at this sort of set here, we have an odd cycle if there's sort of like a loop happening with a odd number of vertices connecting them. So for instance, a triangle is a odd cycle because if I start at this, I can go here, here, and here, but I have like 3 numbers of edges, so it's an odd cycle. For instance, this is an even cycle because I have 4 edges / vertices. Any questions? Great. So now we want to prove the theorem, and I've been having trouble with my if and only ifs, so let's see if we can do it this time. All right. The forward direction is not so bad. So for the forward direction, we're going to assume that a graph is two-colorable. And I'm going to also assume to a contradiction that we have an odd cycle in it. This direction is easy but mildly hand-wavy, but I think you'll be convinced if I just show it to you. So if we have an odd cycle, then we have a cycle that looks sort of like this, or maybe it has 5 points. But either way, if we were to connect these, and I tried to color this with only 2 colors. Okay. Color 1 there, great. Color 2 here, cool. I have a problem now because I can't label this one. I also can't label it 2 because we're connected to both of these. So this is not 2 colorable. Great. Similarly, if I were to, I think I did this example earlier as well. If I were to try and color this one 1, okay, this is 2. So for this one, I don't have a problem quite yet. So I color this one 1, color this one 2. Okay, I can color that one 1. I can do this one 2. But then I have a 1 here, and we run into a problem because I have 2 1s next to each other now. That's not 2 colorable. And I can't really figure out a way to make this 2 colorable. Okay, so if it has an odd cycle, you can't 2 color it. Great. So now we have a contradiction because I have something in my graph that's not 2 colorable, but I said it was 2 colorable. I can't do that. So we have to have that it contains no odd cycles. Feeling good? Great. That concludes our forward direction. Now for our backwards direction. And this one is much longer. Okay. I must review really quickly. Okay, so since we're going backwards, we want to assume that we have no odd cycles, and we want to show that it's 2 colorable. Great. So okay, visuals will be really helpful here, so I'm going to draw some pictures. Okay, here are all of my vertices, and they're connected like this. Okay, this is sort of like a tree or a branch of a tree, if you know what that is. Cool. So we have to show that we can 2 color this graph, right? So we're going to start by just picking like any vertex. I'm going to pick this one and color it black. So if I color that one black, and I have one edge connecting all of the rest of them, then I have to color all of the edges, all of the vertices that are connected to that one a different color, right? I'll call it purple. So this one I can't color black, so I'll color it purple. Can we see purple on the screen? Yes, no? Okay.
Yeah.
Okay, great. So I have to color this one purple as well, and also this one. Cool. So now I have all of these ones remaining, but we have that this vertex is connected to a purple one, so I'm just going to color it black because it's not connected to anything else. So that's nothing stopping me there. And I'll do the same with these two as well. So sort of following that kind of pattern, that's how we're going to prove that this is 2 colorable. So formally, this will be written as follows. First, we note that if we did have an edge connecting any of our purple colored vertices, that would create an odd cycle, and then we have a contradiction. So we know that we can't have like edges connecting each sort of wave of vertices. Okay. So we can't have an edge connecting two neighbors of A. I denote neighbors as NBS because shorthand. Okay. Again, because that would create an odd cycle. So now we need to show that there is no edge between any two of our black colored vertices. So for instance, we would have a problem if there was an edge that connected those two things because now that coloring doesn't work. So we need to show that that won't happen. So need to show. Okay. First, we note that there is, if we note this is U. Please hold. Please hold. Okay, all right. I'm going to skip that case for now and come back to it. Sorry, guys. So I ran into a problem. Okay, so essentially my picture here is now going to be, we have this U and this V, and these are colored the same thing. These are both colored black. Here's U, here's V. It's V. So we want to assume to a contradiction that there exists an edge between them so that we can show that there actually isn't. So assume so because of how our graph is sort of figured out, U will be connected to some dot here, call it U1, another dot here. This one is necessarily colored purple, but I'm just going to leave it open for the time being because of our sort of algorithm that we developed. This will be connected to another black vertex. This will be U2, and this will alternate until we get back to some sort of node here. This will be our original node, A, which was colored black. And this should be open. Okay, so we have this path that we can sort of follow back to our original vertex A. Similarly, we can do the same thing for V. We follow that sort of all the way back to V, and those are alternating colors until we get to here. But this path sort of creates this long path between the two, and suppose we have an edge connecting these two vertices, UV. Suppose that does exist. If it did, we sort of have this concatenated cycle here where this length will be even because it's connecting two vertices of different colors. This cycle here will also be even because it's connecting two vertices of different colors. But because we now have this added edge, we have an odd cycle. That contradicts our assumption. So we know that we can't have this edge here anymore. So that gets rid of that problem. Okay. So now I need to circle back and figure out what I did wrong in my proof originally. Or perhaps you take it on faith. So there is this case that we have to check. I checked it incorrectly the first time. Like do that kind of thing. Yeah. Okay. Right. Okay, yeah, that works. For those that didn't hear at home, our suggestion from the audience, Hannah and Michael, said we could partition our colors into two things, and then if there was anything like connecting each set, we would have an odd cycle, and that's a problem. Similar to this argument, but not quite the same. So if you want, do it at home. Cool. So again, one last thing we need to check is whether or not our graph is like totally colored by the time we do this whole thing. So if our graph is connected, it'll just work. If it's disconnected and we have like two components, one is connected over here and one is connected over here, we do this first one, then we do the second one, then we've done the whole thing. And so we have a two-colored graph. There's another QED, although it feels like a half QED. So question, Michael? Shout out to broccoli. Slav broccoli. Shout out. You rock. Okay. Now, you're right. There is a much easier way to do this. You can just do it by proving the contrapositive. However, doing the proof the way that I've done it gives you an algorithm for how to two-color a graph. And if you can't two-color a graph, then you get you find where an odd cycle is, which is why I chose this proof, because it's kind of cool and neat. And unfortunately, I did one of the parts wrong. So all good. Great. So now moving forward, I'm going to talk a little bit about the Mycielski graph, which I don't know if that's how you actually pronounce that. But I'm trying my best. So there you go. All right. So these kinds of graphs are graphs that contain no triangles and has chromatic number equal to its number of vertices. They're sort of really interesting because it seems like maybe there might be a way to color these graphs with less than their vertex number, but turns out there's not. So I'll just talk about how it's sort of constructed. If we start out with an edge here, and this is my original graph, we can form a Mycielski graph by creating a duplicate of these two edges, or of these two vertices. So we've just created a copy of these vertices, like above it, wherever you want, really. And now what we want to do is connect each of these new vertices with the neighbor of its copy, but not to its copy, if that makes sense. So for instance, because this one's connected to this one, I want to connect this one to this one, but I don't want to connect this one to this one. You do the same thing over here. And then as a final extra step, we have to add another vertex here that has connections to each of those two vertices. So if you're looking at the slides with me, you see that there's like a pentagon there, and this doesn't really quite look like a pentagon, but there's a planar isotopy, which is a fun fancy word for saying if I had strings, if these were just strings and I could like move stuff around and like take stuff out of the board, I could just move this one over here and this one over here, and then I uncross them and you just get a pentagon. So like that's cool and fun. Some topology for you. It's great. Cool. So now I want to do like the same process but with this graph. And so the way that we do that is, first of all, we draw those 5 vertices and their connections. So now we want to make a copy of each vertex that we have already, namely these ones. And for this construction, we need this node to connect with each of these two because that's what its duplicate is connected to. So we'll connect those. And the same sort of pattern follows for each of these. I've drawn this slightly poorly, but that's okay. Great. And so now our fifth sort of task is to add a little dot here and connect them to all of the copies that we made. And we end up with what hopefully looks like what's on the slide. And I would say it does. So that's sort of our construction of the Mycielski graph. And the interesting part about this is that these graphs have, nope, great. I think that theorem was, oh, right, haha. Okay, first of all, it contains no triangles. Second of all, its chromatic number is equal to its number of vertices. So, inwards. So this one has 1, 2, 3, 4, 12, perhaps, vertices. So it would have K coloring less than 12. Anyway, this one has 5, though. That one's easier to count. The reason these are so interesting is because it kind of sort of like contradicts an intuition that we might have. Like, we might think that this has a coloring of less than the number of vertices just because of how many connections are happening. But it turns out the answer is no, and the proof is quite long and arduous, so I shan't do it here. But should you look it up, it's easily accessible. Okay. So now, what do I want to talk about? I want to talk about planar graphs. Okay. Here you go. We have a definition for you. We say that a graph is planar if it can be drawn in the plane without crossing any of the edges that are connecting our vertices. Seems simple enough. Here's an example for you on the slides. You'll notice that none of our edges cross over each other. That's a good thing. That's what we want. Great. Any questions about what a planar graph is? Feeling good? Okay. Cool. So what's so fun about them? A lot of things, actually. In order to talk about planar graphs, we need to to talk extensively about planar graphs, we sort of need something called the Jordan curve theorem. And if you're a math person, you've probably heard of this guy. It's pretty important. In my field of topology, it's super important. Basically, all this says is if we have a simple closed curve C, and by simple, I mean it doesn't cross over itself. So if I have a curve that looks sort of like this and sort of also returns to the same point, so for example, a loop, this will partition our plane into two connected disjoint open sets, just meaning that this whole thing is a set and everything outside of it is also a set. Everything in here is connected and it's totally disjoint from everything out here. It feels intuitive, but I'm going to tell you this proof is terrible. This proof is not fun to do. The shortest one I have ever found was 3 pages long. Here it is. If you're super interested, you can go and find it. And in fact, this isn't even a graph theory proof of it. This is just the shortest sort of using topology and analysis type stuff. So you'll need some extra background. But yeah, so I'm not going to make you sit through all that. If you're interested, let me know and I can send this to you. Yeah. And Michael says this counts as a QED. I don't think I'm going to count it, but yeah, half tally. There we go. Right, yeah, we can't have half tallies. It's everything or nothing, so I'm going with nothing. Okay, so there's proof if you're curious. This is super nice for many reasons, and one of them is that it helps us figure out this problem. So this is graph theory. We're probably going to want to make this ugly word problem into a graph, right? So our problem statement says that there was once a king who had 5 sons. He had all of this land. And in his will, he said that he wanted his kingdom to be divided into 5 separate pieces for each of his son, but all of the pieces should share a border. The question is, can we do this? I don't know, can we? So I'm going to model this as a graph. So if we have the whole land and we have 5 sons, we need 5 vertices, right? Or 5 parcels of land to be divided up. But we need the property that every one of these pieces of land has a border connecting them. So that's what my edges are going to be. So this needs to be a totally connected graph. All of the vertices are connected to every other one. And I think that does it. Yes, that does it. Great. So if you're interested in notation, this is a K5 graph. All it says is we have 5 vertices and all of them are connected. And that's how we denote that. Cool. So I'm going to argue that we can't fulfill the king's wishes. He's already gone, and his last dying wish is not going to be granted, unfortunately. So let's prove it. Kind of prove it. Suppose that this is planar, and we can really do this. So great. If it was, we can consider a drawing of this thing where none of the edges cross. I would attempt to draw that for you, but I'm not going to. So instead, what I'm going to say is if we have, inside of this planar representation of this graph that we are supposing exists, we're going to have this triangle sort of looking thing where these 3 things are connected to each other. by some sort of border, right? Cool. I'll call this V1, V2, and V3. But we still have two vertices to contend with. So where do we put them? Vertex 4 is going to have to go either inside or outside of this thing. It doesn't matter which one you choose, it turns out. So I'm going to choose that it's inside. Here's V4. Cool. We also need the property that V4 is connected to each of these things by some sort of border. Cool. It's a very fun looking piece of land so far. And now we still have this fifth vertex to deal with. And so we have multiple options kind of where 5 can go. But I'm going to say it goes out here. We could choose that it goes inside one of these regions, but simpler to draw it out here. So here's V5. Great. So I need to connect V5 to every one of these other vertices. Cool, let me try and do that. Great. Getting some really weird shapes of land. It's not connected to V4. And if I tried to, in any way, I would have to cross this sort of line to connect it to V5, which breaks our definition of planar graphs. Not cool, can't do it, very bad. And the reason this works is because of our Jordan curve theorem. If you'll notice, our initial sort of weird triangle looking thing was this or something. This forms a simple curve in the plane. And so now our plane is partitioned into this side and this side. And if I have something in here, it's completely disconnected from anything out here. So because I was forced to place my V5 outside or in one of these regions, similar argument follows, we have to cross this curve, but Jordan tells us, no, we can't do that. Cool. Any questions?
So if we had 4 princes, we'd be good?
Believe so, yeah. Yes. Cool. All right, any other questions? Yes. Right, so we need, yeah, good question. If I have like all of these chunks of land, here's one chunk, here's another chunk, here's like a third chunk over here. I'll do it as a grid because it's easy. Okay, so I have these 4 chunks of land, and really what I want is 5, but because I can't, we just showed that I can't actually do that, I'm gonna go with 4. So we have these 4 chunks of land. I want all of them to sort of share a border with each other one. So like if I'm here, I want at least one part of the edge of this square to touch every other square. And similarly for the other 4. And so a thought that I had when I was doing this problem the first time around is I was like, okay, what if I had like a square here, like a 4 corners type situation? But then we run into the problem like, okay, we have 5 squares now, but this square doesn't share any common edges with this square. So that's our problem. Yes.
So if we were to allow them to count corners, we'd be totally fine. Or if we were allowed to allow our princes to have territory that wasn't contiguous, we'd also feel.
Yes, exactly. Like if we said, okay, this square can have a little piece of this territory, then you're fine. But we want all of our pieces of territory to be like sort of compact.
We don't want a Berlin Wall going.
No Berlin Wall situation. Yeah.
Before you drew the square in the center, with your grid thing, so like sharing a corner, because like I would say like they share like the diagonals share like a fence post essentially, that counts?
It counts.
Okay, cool.
As long as some point of their boundary is connected at some point, like that point counts.
Yeah, then if you have the square in the middle,
It doesn't work anymore. Yeah. Other questions? Yes.
Then wouldn't you be able to create a radial of the
I'm not quite sure what you mean by that. Well, I will say a pie with 5 slices, if you will. Yes, I suppose so. Well, I'm going to say that we can't do that by this theorem that we have, but I can't tell you why right now. That's a good problem to work out, is it? Yeah, we can't count corners. So what I've drawn here is like bad. Anyway, what I mean is like all of the pieces of land need to share a border somehow with each other. Cool, great. Any other questions? Cool. So from this, we learned that this graph is like not planar because we can't draw it without crossing the boundaries. That's what we learned. Yes? Yes?
But this kingdom doesn't exist on a plane. This kingdom exists on a sphere.
Excellent question.
Could we maybe just take over the rest of the world to fulfill the king's wishes?
That is an exercise left to the reader. So, yeah. All right. So, great. Now I probably like want to figure out a somewhat easier thing to use than the Jordan curve theorem, especially because like I didn't prove it for you, so you're just taking it on faith right now. So instead what we're going to use is what's called an Euler characteristic to prove sort of the same kind of things that we've been proving. Oh, first, sorry, I forgot to write this up. All right, so the whole like sort of spiel about pi day is like we like to give you some conjectures that you might be able to work on. So the way that I've drawn these boundaries, they're not straight lines, but we have this theorem that says if G is planar, if we have a planar graph, we can embed G in a plane in such a way that all of my lines are actually straight on the graph that I've drawn. So because this isn't planar, I can't do that without crossing edges, but say we did have a planar graph, we can draw sort of the graph on the plane with just straight lines instead of curves. Cool. So sort of a conjecture that's still open that maybe you want to work on is that every planar graph has a planar embedding where every edge is a straight line segment of integer length. So because this is like just graph theory, we don't really talk about the lengths of edges and things, but geometers are interested in that kind of thing. So there's this conjecture that says, okay, we have this planar graph. I want to be able to draw this planar graph with integer length segments. It's not proven yet, but it feels true. So if you can prove it, that'd be great. Cool. Any comments, questions, concerns about this one? I can't really answer anything because it's not answered, but cool. Yeah, you know, I'll just, yeah, on the spot. It's worked well so far. Okay, now we can talk about Euler characteristics. Great. This is another really fun one, also used in topology quite a bit. And I'm a big fan of that. So the definition of our Euler characteristic is if we have a planar graph with v number of vertices, e number of edges, and f number of faces, then we have that it satisfies the equation the vertices minus the edges plus the faces equals 2. This is actually a really cool property. I can't really talk about it because I don't have time, but it's super fun. Anyway, so what I mean when I say a face of a graph is, do we agree this is a planar graph? I've drawn it in a plane and none of the lines cross. Cool. So the number of vertices in this graph is 3. Do we agree? Cool. So that's V. The number of edges is also equal to 3. And a face is just anything that's enclosed entirely by edges. So this would be a face. For example, if we had like more vertices over here, this is a separate face. Other questions? Cool. Okay. So now I get to prove it for you. Oh wait, no, I want to go for it. Anyway, the typical proof for this involves induction. I'm not going to do it by induction because that comes later, and I don't want to do it that way. In fact, there's a way more fun way to do this, and it's going to call back to our Euler tours. Super fun. Okay, so what I'm going to prove this is that if we have a tour, we can sort of like manipulate it in a way to get this out of it. Great. So we're going to recall that a connected graph has an Euler tour if and only if every vertex degree is even. this we proved earlier. If you weren't here for it, it's in the slides, which you can find somewhere, I'm sure. Okay, so, all right, given a tour, we're going to let R denote the number of times vertices are revisited after their first visit. So like if I have this vertex here and I somehow ended up here and like I go around and like, okay, I come back here, I leave again, I come back here. My R is going to be 4 because I revisited this vertex 4 times after I initially started visiting it. Cool, great. So now that we have that, it's going to walk around the number of edges like once, right? So the maximum amount of times that a vertex is visited is going to be the number of edges plus 1. So and it's important to note that the number, okay, so it visits it this many times, but the number of vertices many times is visits for the first time. That's hard to explain, but maybe it'll help to write it down. Of these visits, cool. So then, since we let R be what it is, we can write that R is equal to the number of edges in our graph plus 1 minus the number of vertices in our graph. Okay, this is one way we can write R. I want to find a different way so we can like back substitute in and get some cool stuff. So suppose G is planar and it has F faces. Okay. Then we also have to have that the number of faces is equal to R plus 1 because if we look at R, this is going to give us the number of edges plus 1 minus the vertices. If we add another one, we get plus 2, and our faces are enclosed by a certain number of edges plus a certain number of vertices, and that's sort of how we get this sort of formula. Just like sort of trust me on it, I guess. So, okay. Now we want to start, okay. If our graph has n vertices, to be clear, that's this one. Okay, we're going to say that G has n number of vertices, m number of edges, and f number of faces. Then we can replace each edge of G with 2 copies of itself. So like if we're, here's an edge in G, we're just going to add another edge here to get 2 edges on each one edge that was originally there. So create. And so when we do this, each time we do this, we're adding another face that is enclosed by those 2 edges to our graph. So if we do that over and over again until our whole graph has done that, our new graph G prime is going to have twice the number of faces that we did originally, or no, twice the number of edges that we did originally, and then f plus the number of edges of faces. Great. Also, if our vertex didn't originally have even degree, because we doubled the number of edges, we now have that all of our vertices are of even degree. So we think back to, like, we have an Euler Tor now on G prime because that's what our conditions call for. So we can write that for our new graph G prime, we have that R is equal to 2m plus 1 minus 2v because of this formula here. So our number of edges is now 2m plus 1, and then minus the same in amount of vertices. Great. We also have that from this formula, our number of faces is now f plus m, and that's going to be equal to r plus 1. So now we can solve for r here. We're just going to place this in for r. Anyway, I said that backwards, but we get f plus m is equal to 2m plus 1 minus n. Cool. Now we're going to rearrange. Plus 1. So we simplify and we get f plus m is equal to 2m plus 2 minus n. I'm just going to move everything to the other side. So we get f minus m plus n is equal to 2. And if we recall what the Euler characteristic is, it says the number of vertices minus the edges plus the faces is equal to 2. And so that's our fun little proof that's kind of nifty and cool of the fact that the Euler characteristic really works. Yeah, it's super fun and cool, right? Like, I don't know, you can do this by induction and it follows somewhat easily, but it's not as fun. Like, this is super cool, and like, shout out to the guy that made this. I think he was an undergraduate student, and he was like, I think that the Euler characteristic and the Euler tors must be connected because the same dude did them. And previously, nobody had like figured out how the connection really worked. And he did this, and it was really sick. I wish I had his name, but I don't. I'm sure you could find it somewhere. So yeah, cool. So that concludes my proof of the Euler characteristic. And up next, I'm going to skip actually the next slide. Yeah, so we have this problem, the three utilities problem. It can be proven using, or disproven rather, using the Euler characteristic. However, for the sake of time, it is in fact 11:05, and I've got still quite a bit to get through. So I'm going to skip this. However, if you're interested, come talk to me afterwards. Great. But I guess I'll just state the problem anyway. So the three utility problem says, like, okay, we have these three houses, and we have these three companies. So here's house 1, 2, 3. Here's our water, electric, and gas company. And we need that each of these houses is connected by a line to each of these companies, and the lines have to be separate for some reason. So we get this graph. We've seen this before. This is the, for people who like notation, this is the K33 graph. That's what we call it. And so by doing this problem, you sort of prove that K33 is not planar, because it turns out we can't actually create a graph that has all these connections that doesn't cross itself at some point, basically. And the way you prove that, or a way to prove that, is using the Euler characteristic. But I'm going to skip through that proof because it's a little bit lengthy.
K3 and K5.
Yeah, are not planar. Yes, yes, I think, yes. However, I'm not going to talk about it right now. Okay. So, moving on. using our Euler characteristic, we can just like talk about some platonic solids. A way to think about this is just like a dice with a number of faces. If you're a D&D fan, you know about these things. So we say that platonic solids are regular polyhedra, but that just means that all the faces are the same size and also the same shape. So the exercise here is to show that the Euler characteristic actually holds for some simple solids. So I'll do, first of all, the tetrahedron. Tetrahedron, for those of us who might have forgotten, is like a pyramid. And looks like that. That's a dotted line. Cool. Here's a tetrahedron. Great. I want to prove the Euler characteristic, which again says that the number of, I always have to check. Vertices minus edges plus faces is equal to 2 if it's planar. If I can draw this in a way where it's like flat on the page and also none of the lines intersect, then we're planar. Cool. We can use the Euler characteristic again to do that. So if I'm just going to like count what's going on here, the number of vertices that I have is 1, 2, 3, 4, 5. Everyone's with me on that page? Great. The number of faces is also going to be 5 because we have this front face here, we have 3 others in the back, and then the bottom face. So face is also 5. So now we need to determine the number of edges. Sometimes this can be like weird because if you're like thinking about different kinds of shapes, you might be inclined to double count some edges, but we don't want to do that. So, but here we can just look at it. Okay, there's 4 edges here, and then 4 other distinct edges here. So the number of edges is equal to 8. Yes. Okay, so now we just apply our Euler characteristic to make sure we really can draw this in the plane. So what we do is, take 5, subtract the number of edges, which is 8 from it, and then we add 5 back because that's the number of faces. Is this equal to 2? Simple math. Yes. It should be. No, it's good. I also thought the same thing. I was getting concerned a little bit. Cool. Because, yeah, my head was like, the 5s cancel. No. Anyway, so this really does equal 2 because we get -3 here, and then we add 5 back, and we get 2. Cool. So you might be wondering, how do I actually draw this thing in the plane? I'm going to say, if I have this pyramid is on the ground, and I like just sort of like stomp on it so that the top vertex is now on the ground, we end up with a graph that looks like this. This is sometimes called the projection of a graph, or the embedding, projection for me, embedding for you guys, of this graph here. So we have a vertex at each of these corners. And this is our top vertex. So if you imagine like looking at this from a top-down view, this is sort of the view that you get. So this is our planar embedding. Cool. Questions? Great. I also have like examples for cube and octahedron. Octahedron's kind of fun because it feels less obvious that you can embed it. So I'll do that one. An octahedron is just like this with a copy flipped over. So do this. Okay, terribly drawn, you get the idea. It's that flipped over and glued together. I'm not an artist, it's okay. So now this will be a little bit harder to count, especially because I've drawn it so poorly. But the number of vertices here will be 4, and then 5, 6 for each of the points there. Are we believing me there? Cool. So vertices equals 6. The number of faces is going to be 8 because we don't really count this face in here. Do we? Maybe we do. It's inside, yeah. No, we don't count it because it's inside. It's not a face, it's inside, duh. Okay, so we have 4 edges on each side, and we don't count this one, and we like flip it over, so we get 8 faces. Do we believe me there? I didn't believe myself for a second, but that's okay. Faces is 8, and so now we need to determine the number of unique edges. I'm gonna say that there's 4 here, there's 4 here, and there's 4 here. 4 times 3 is 12. Cool. All right, now we want to apply the Euler characteristic, which says it should be 6 minus 12 plus 8. This should be equal to 2. 6 minus 12 is -6. Add 8, you get 2. So this tells me that I should be able to draw this on a plane in a way that none of my edges cross each other. This one is less obvious. In fact, I don't even have the picture here drawn. Easy to find online, however. If you just smush it down, and then that doesn't work. Push it in. Push it in. Wait, yeah. Okay, so it's like this way. Anyway, I'm not going to draw that because it's a lot. But yes, question.
Rotating it, triangle.
A triangle on the top and bottom, like here and here?
Yeah, if you rotate it.
Oh, I see what you mean. Yeah. Yeah, that works. Cool. Like smush it. Yeah. Cool. Okay, so this is planar. We can draw it in the way that you suggested, or the way that Hannah suggested, which should be the same thing. Yeah, so any further questions about these examples, at least? Cool. Yes, no? No. Great. All right. All right, now we have another problem. We've just said that platonic solids should have a nice Euler characteristic of 2. So now we're going to do it for the D20. Great. So this is like the formal name for this is a regular icosahedron, and I always get that confused with some other word that is a different shape. But it's a polyhedron with 20 triangular faces. So we want to find the number of vertices in the regular icosahedron. I want to say isodecahedron, which is not a real word. Anyway, so we have that the faces is 20, and the number of edges on each face will be 3, right? So each face is going to have 3 edges. However, each face is going to have 2 shared edges. Like we're going to double count 2 edges for each face. So if we were to just say, okay, like the number of edges is 20 times 3 because that's how many edges we have, we would get that that's 60. But again, like we just said, we are counting those with multiplicity and specifically with multiplicity 2. So we have to divide by 2, and we get that the number of edges is 30. There's something coming up that might help clarify this. And we know that vertices minus edges plus faces should be equal to 2. So like if I want to find the number of vertices and not just count them, how would I do that? Just plug it into the equation. So I know that my faces is 20. Solving for vertices. I know that my edges are 30 and faces are 20. We want that equal to 2. Just solve for v, and we get that the number of vertices is going to be equal to 12. Not 2, 12. So all this is just like applying the fact that we know that this is we can represent this in a planar graph and using the Euler characteristic. Further questions? No? Okay. Great. So that's my final little example for this. Now we get some fun like bounds and things. So our first theorem says that a planar graph with e number of edges and v number of vertices has the number of edges less than or equal to 3 times the vertices minus 6. So here's our proof. This is like sort of a manipulation of the Euler characteristic in a way. So suppose G is planar. We also want that it is connected and has F bases. Cool. So we can count the number of edges in G by summing the number of edges that bound each face, which makes sense. But we just said that each face is bounded by, so like, okay, in order for a face to exist even, like we can't have a face between just 2 points. We have to have a third point. And like if we had 2 edges, that's also not a face. So we need at least 3 edges to make a face on anything that, like any sort of graph that we have. Does that make sense to people? Cool. So, so f in this case has to be bounded by at least 3 edges. Each face is and each edge should be counted at most twice, just because of how layouts work. But so we know that 2 times the number of edges of G should be greater than or equal to 3F. Cool. And again, that's because like each face will have at most 2 shared edges. So that's where we get this sort of factor of 2 coming from. So then we just like, you know, move stuff around and we get that the number of edges has to be greater than or equal to 3F minus 2. That's not right. Divided by 2. Because algebra, right? All we did was divide by 2. Great. Cool. And so since we have that G is connected and planar, we can apply the Euler characteristic to it. So that's going to tell us that, so our general formula, once again, is V minus E plus F is equal to 2. This implies that V minus 2 is equal to E minus F. Again, this is just like me moving stuff on either side of the equal sign. Great. And so now I want to back substitute in the stuff that we know. So we know that this has to be greater than or equal to this. So we get that this is greater than or equal to minus 2/3 E. This I'm just getting from the fact that like you can take the reciprocal and get F instead of E. Cool. And so this is precisely equal to 1/3 E. And so this combined with this over here means that V minus 2 is greater than or equal to 1/3 E, which implies that E is less than or equal to 3V minus 6. Questions? Yes. What about loops? They must be accounted for in this. Like it must still work. As long as it's still planar.
Yeah, okay.
Yeah. Like we'll just add an additional face, you know what I mean?
Lower the edge.
Oh, lower the edge. Well, that's why it's greater than or equal to. No? Yeah. Yeah. QED. Great. The question raised was, what if we had like a double edge here? Then it would lower the number of edges that we're assuming, but because we have this greater than or equal to sign, we're fine. Like it still accounts for that case. Cool. All right. Any other questions on this? It's just some calculations and looking at stuff. Great. Okay. So my next proof is that K5 is in fact not planar. We remember K5 from the 5 princes problem. And I'm going to use a different proof this time using Euler characteristic. Let me change slides. Oh, never mind. Hannah got me. All right. So it's sort of just a corollary of the Euler characteristic. ER1. That K5 is not planar. So I'm going to do this proof by contradiction. We're going to suppose that it is planar. To be specific, suppose K5 is planar. By our corollary that we just proved, we know that the number of edges has to be less than or equal to the number of vertices times 3 minus 6. So we get by our previous corollary. So we know that K5 has 5 vertices, which means that this here is going to be equal to 15 minus 6, which is 9. I was going to say 11, but it's not. And we also know that it should have 10 edges. Just as a reminder, it's this one, like the pentagram situation. Cool. We count these up, that's 10 edges. So we know that that is going to be equal to 10, but then that tells me that 10 is less than or equal to 9, which violates my previous corollary that says that it's planar if this thing is true. So we know that K5 isn't planar, and this is a much simpler proof, in my opinion, than using the Jordan curve, which is why Euler characteristic is so nice. Other question? No? Feeling good? Great. Okay. We have another corollary for you. That every planar graph has a vertex of degree at most 5. So the proof for that one is as follows. So suppose there exists a planar graph with all the vertices having at least 6 edges connected to it. This will be a proof by contradiction, in case that was not clear. Suppose there exists planar graph. Cool. So now we're going to make a callback to the handshaking lemma. Hooray. By the handshaking lemma, we have that the number of edges should be equal to 3 times the vertices. By. Great. And we should also have, by our previous corollary, that E is less than or equal to 3v minus 6. But like E being equal to this and also being less than or equal to this is a contradiction. This will never be true. Well, for the numbers that we care about. So we've reached contradiction. So we have that there must be at least one vertex of degree 5. Questions about how we got here? Feeling okay? All right, cool. Now, we're getting to the, oh, there is, in fact, another QED. Really racking them up. Okay, so my next problem is going to be to show that a planar graph is 6 colorable. We're really getting to the meat of the issue here, where we want to go, if you recall from Cory's statements at the very beginning, is we want to show that like a country, like countries can be colored with only 4 colors where none of the colors are like adjacent to each other, right? And so in terms of like graph theory problems, what that really says is like, we want to show that any planar graph is 4 colorable. Well, here's our first step. We want to show that any planar graph is 6 colorable. Cool. So the way that we're going to do that is as follows. Great. So by our corollary that we just did, we know that every planar graph has a vertex of degree at most 5. Graph has. Cool. This is what we just proved. So now we can also recall our greedy bound problem that we did forever ago that says we have for graph G a proper coloring of degree at most highest degree of a vertex in G plus 1. If we recall that one, it's from like, I don't know, an hour and a half ago. So, okay, cool. Well, because we know that every planar graph has a vertex of degree at most 5, and we can say, okay, probably our degree of G is going to be our delta of G, which remember was the highest number of edges connected to any vertex in our graph, is probably going to be equal to 5. Cool. So by our greedy bound problem, G can be colored with 6 colors, which says that exactly what we want to show. Great. I will say there's a little bit of like hand waving that I'm doing right now to be really thorough about things. We could potentially have a graph. Here's my graph where I have like vertices, whatever, that are connected by 6 edges, like they're connected to 6 other vertices, right? So 1, 2, 3, 4, 5, 6. So this one. Okay. So suppose I did have that. Just take one of the vertices out, is I believe how we do this. I haven't looked at this one in a while, but I believe what we do is we take out a vertex, and then suddenly, by our assumption, we can 5-color these. And so, well, if you add this thing back in, we can add a 6-color, and then it's 6-colorable. And that's really hand-wavy, but that's the general idea. Cool. So now is my longest, most important, probably, proof of the day. We want to show that a planar graph is 5-colorable. Again, working our way towards the idea that every planar graph can be colored with only 4 colors. So the way that I'm going to do this is sort of informally induction. I don't want to do it super formally because y'all will get to that later, super exciting stuff. But the sort of like idea behind this proof was done by a dude named Kempe way back in like, I want to say the 1800s, like early 1800s. And this proof feels like it should work for 4 coloring, but it actually doesn't. And I'll say more about that once it's proven. So suppose we have a planar graph with n vertices. Cool. So because I'm sort of informally using induction, the way that we do that is like we assume that what we want to show is true for n, or I guess in this case, n minus 1 vertices, and then we want to extend that to the case where we have n vertices using some techniques. So our what is called base case, or inductive hypothesis, I guess, is that a planar graph with vertices less than n are 5-colorable. I can spell. Okay, planar. Okay. So now we want to use this inductive hypothesis to show that a graph with n vertices is also 5-colorable. Yes. Yeah, I'm getting there. So actually, I might not have a formal base case for you. We're just taking this to be true. Yeah. Okay. With this assumption, we also know that we have a vertex in here with degree at most 5 by one of our previous corollaries. So we're going to end up using that. Okay. So we're going to consider sort of 2 different cases. This is technically a proof by like least counterexample. So case 1, if our vertex has a degree of 4 or less is going to be what we first look at. Then we can delete V from whatever graph we have. I'll draw a picture in a second. Then once we delete that, like whatever graph we have remaining, we know we can 5 color because now we have a graph of degree less than n. Cool. So V also has at most 4 neighbors here because its degree is less than or equal to 4. So because this is true, like here's V, and here's the 4 thing it's connected to. Once we delete V from this graph, like these will have 4 colors connected to it that are colored in a 5 colorable way because of how we structured our argument. And then once we add it back in, we can find a 5th color that will extend to V. That concludes case 1. Are there questions here? No? Great. Okay. Case 2 is sort of fun, I think. So here we need to concern ourselves with when our degree is precisely 5 for our vertex because we've covered all of our other cases with case 1. Okay, so actually, we're going to sort of do it in like a weird contradictory kind of way. What ends up happening is we're going to say every vertex is of degree at least 6, and then we're going to show that that can't be true. Okay, so now what we're going to do is say that, okay, we have this thing from earlier, it was our corollary that said 3 times the number of vertices has to be greater than 3 times the vertices of G minus 6. Yes, minus 6. And this was used in a corollary earlier that we showed, and anyway, we've seen this. So it will have this many edges. But that will violate the fact that it's planar, so we can't have that every vertex has degree at least 6. So like now we can rule all of those things out. So we try to prove for 5. Contradiction. So there must exist, by this, a vertex of degree 5. Cool. So now I'm going to draw some pictures and they'll be really helpful. So say that this is the vertex that I'm concerned with. Here's X. And if X has degree 5, then we have 5 other nodes that are connected to it via edges. 3, 4, 5. And specifically, these are all 5 colored. So we'll note that this is 1, 2, 3, 4, and 5. So these are colored in the following way. Okay. So and like it's important that they're arranged this way specifically. So if we consider G minus X, like we just take out this vertex from the graph, then we're left with a 5 coloring. Cool. All of these are disconnected now, so like maybe we can swap some things around. So this is 5 colored. And all of our things have different colors. If 2 of these vertices had the same coloring, it would violate the 5 colorability if we had X in there. So we know that that can't happen. I'm missing a step here, I fear.
I think the other way around, right?
Yeah.
If those were colored with repeated color, finish the color.
Right,
This
yes.
would be a case 1.5.
Yeah. So like, okay, yeah. So if we took these out and these 2 were the same color, and then we added X back in, that would violate color, like 5 colorability. That's what happened. Sorry, got
Or not
confused.
violate, you would succeed in coloring with
Oh.
colors, right?
Jeez, yes. 3 hours in, you know what I mean?
Exactly. This is the
Yeah. So, okay, that's our case. All right. Okay. So we could 5 color in that situation. However, we need to consider a subgraph now. I'm going to erase case 1. Are we cool if I erase case 1? So we want to consider a subgraph of our big graph G that only looks at the points that are colored with the color 1 or 3. So I'm going to note this as okay. So if I do this, then what can we do? There are a couple of different cases here. So we could have that we have this vertex here that's colored 1 and this vertex here that's colored 3. So both of those vertices will be included in our new graph that we've induced now that we have just chosen those. So either there's a path that connects them or there's not. So we're going to show that there has to be. It could be possible that they're in different components, like that their paths are disconnected and that we have some path 1, 3 and then like some other path 1, 3s and they never cross paths. They're not connected at all. So could have that. If they are in different like components, then we could just like change this 1 into a 3 and not break 5 colorability on our, or like will not break the chain of 1, 3 colored dots in our bigger graph. So like what I'm imagining here is here we have a 1, it's connected to a 3, and this is connected to a 1, and this is connected to a 1. It's connected to a 3, but these paths are never, like, they never get connected at any point in the graph. If this is the case, then I can just change this to a 3 and then swap every 1 and 3 along that path so that we keep coloring nice. Okay. So if this is true, okay, so we do that.
Well, can I ask you a question?
Yes.
So you swap those 1s and 2s?
Excellent question. Well, because we're only considering the subgraph with 1s and 3s in it, like we kind of don't have to concern ourselves with those. And because like in the first case, this was a 1, this was a 3, and this was a 1. Suppose this was connected to a 4. If we change that to a 1, nothing's going to change. It'll be fine still. Like it will still be 5-colored in the grand scheme of things.
As long as you're swapping all the ones.
Exactly. It'll be okay. Yeah, you won't cause any problems. Great question. Thank you, Cory. So, to make sure I cover everything. Right, so that doesn't affect our 5-coloring of the whole graph, and so like everything's fine. Great. So, if we can do that, where we really did switch all these numbers, this is now a 3 and a 1 and a 3, then X is only connected to 4 other color components, which means that there's a 5th color that we can apply to X that won't break 5-colorability. So cool.
Not even a mystery, right? It's literally 1.
Yeah, it would be 1. Yes, indeed. So if we did in fact make this a 1, now we can turn that into a 1, but now we've connected this thing. It's fine. Our 2 colorability of the path that we're concerned about, which is the 3-1 path through this point X, which is now a 1, has that this is connected now. And so 2 previously disconnected paths are now connected, which is interesting because now we can sort of like, I'm going to say this and you can try and challenge me on it if you want, but I'm going to say there's some series of path that will connect all of it. So like if this was originally disconnected, we're going to end up with a really big loop. So now I'm going to call back to the Jordan curve. This creates a Jordan curve in the plane. What we've done here is now we have this loop that sort of sections off the plane where all of these points are connected somehow, but partitioned off from all the points outside of this curve. That's important right now because if we were to consider a similar sort of case for the subgraph of 2 and 4, what happens then? Trying to decide what can be erased. I guess I'll just go up there. Cool. How am I doing on time? Oh, not bad. Okay. Okay. So now we want to say consider the subgraph where we're only looking at 2s and 4s. So like this is part of that. So is this. So if we were to construct a 2-4 path in the same way that we constructed this 3-1 path, i.e. like swap this to a 4 and try and make a loop back around, we would have to cross this thing. Well, yeah, like it would be, I could try and go any sort of direction, but because I have that this 1-3 curve cuts off the plane, like I can't cross this and still be planar. So by the Jordan curve theorem, this would violate planarity.
Can I ask a topological question here?
Yes.
So this Jordan curve is really the union of a bunch of segments that probably some easy result, right? That if you concatenate some. Actually, what are those individual curves? They're not closed, right? The edge when you draw them. Is that a Jordan curve?
So, well, you only get a Jordan curve if you like close off the whole curve.
You have to close it off.
Yeah.
So what's just a segment? Yeah, like what's a series of couple of edges? Does that have a name?
I think it's just a path.
A path, right? In both.
I think so. Yeah. I haven't heard it called anything otherwise.
So like the concatenation of paths that close, I mean that's some theorem. That's a Jordan curve, presumably.
Probably yes.
Yeah, I mean, yeah, I don't mean to.
No, like
it's obvious it should be.
Yeah, I think it's probably pretty easy. Yeah. All I'm thinking about is like concatenation of loops right now because that's what I'm doing in my class. But anyway, yeah.
It's nice because this will be a finite number of
exactly.
them, so they're not gonna have weird.
It's probably like induction kind of thing.
Yeah, maybe. Okay.
Cool. So, yeah, this would, if we did the same thing for a path with 2-4, it would violate the planarity of G, because we would, by the Jordan curve theorem, we would have to cross this sort of like already crossed off section. So we have to have, in that case, that 2 and 4 are in different components, right? This forces that. Y2 and Y4 to be in different components. And so because this is true, we don't really run into any problems trying to 5-color everything else. It sort of blocks off the possibility that we might have 2 colors right next to each other because we have to have these are in different components. You could make the same argument for 2 and 5. It's equivalent. But yeah, so as a combination of all of these things, we get that since X is connected to 4 different colors, we can color it with another 5th color. And so our planar graph is 5-colorable. And that's, yes, right.
Although you could go up top and transform 4 into 2.
Yeah, you could do this. You could switch it either way. It doesn't matter.
The point is they can't flip each other simultaneously.
Exactly. Yeah.
All right, I took the point.
No, you're good. So, all right. You might be wondering, like, okay, why do we care? This kind of type of proof was what was believed to be the proof of the 4-color theorem for a long time, and it like wasn't even challenged until I think 20 years after it was proven this way. So this sort of argument like feels like it should work for 4. Like, why can't we do the same kind of thing? I forget the exact picture, but essentially we don't end up getting a nice Jordan curve like this. Nothing gets really barred off when we try to do 4-colorability this way. And so because that doesn't happen, we can't use this kind of proof to show that any graph can be 4-colorable. That's sort of the punchline of everything. However, I will say that the 4-color theorem has been proven. It's not a conjecture. It might feel sort of improbable. By the way, the 4-color theorem is as follows. A planar graph is 4-colorable. And so essentially what this says is like, if I have a graph and I can smush it down onto a plane and none of the edges cross, like I can color those vertices with just 4 colors and have it fully colored. Sort of crazy to me, especially for like huge graphs. And if we think about like maps and stuff, they use this to color maps all the time. World maps and countries and things. So it seems improbable. And the first proof, I think, the first real proof of this was done by a computer in the 60s and 70s. And it was just like brute forcing a bunch of cases to show it was true. And in fact, like the first proof of this theorem was kind of the first proof ever to use that sort of computational power. And so when it was proved that way, people were like, I don't know, you guys, it kind of feels like there's a lot of computation here that I can't really check by hand, and I'm scared of that. It turns out it worked. And then I think like 20 years later, in the early 2000s or late 90s, I can't remember which one. Anyway, sometime later, the initial algorithm for the 4-colorability theorem proof was in quadratic time, which is like long and arduous. But this new proof, they condensed it down and got it into quadratic time, which is pretty good. And so once they had done that, people were like more comfortable also with like the passage of time, people were more comfortable with computational proofs. But yeah, so that's sort of like the general history of how we got to the 4-color theorem. Are there questions?
Yeah, you had a 6-colorability of planar graphs?
Yes, we did.
5-colorability of planar graphs.
And 4-colorability.
Why is there no 3-colorability of planar graphs?
Good question. Why?
Can you draw a tetrahedron?
Yes. In fact, I can't draw, we determined that I can't do the next up of this one. Like I can't stack it, but I can draw it.
Right. There's a particular. Oh, I see. Okay.
Yeah.
How about the projection?
Right. There you go. I did stomp on it earlier.
That's not quite that thick. That's a 5-vertex graph.
Oh, yeah.
So I think you want a triangle bounding the outside, single vertex inside. I think at the 4
Yeah.
side.
Yeah. Triangle, vertex. There, like that. Yes.
What's the chromatic?
It's 4.
Yeah, you can't.
Yeah.
You can't. It's a complete graph.
Yeah, it's a complete graph.
So it can't be a 3-color. Right. There are planar graphs that require. Some
So it's
require
like
3, some require 2, but the lowest you can have a general.
Cool. Nice. QED. And that concludes my section of Pi Day. So, yeah. Thanks, guys.
Thank you, Molly.
Thank you.
Clap for Molly.
Okay.